Yeah, one of you please confirm my screen is visible.
Yes, sir.
Yes, sir.
Thank you. Thank you. Yes, today is the today we shall discuss the tutorial sheet 10. It is no lecture, but this is a common tutorial discussion session. So starting with the question number one. Okay. Uh, the problem one says that prove or disprove every component of the symmetric difference of two matchings is a path or an event cycle. So we have a graph, and if we have given two matchings, then their symmetric difference. Suppose M and N are two matchings, then their symmetric difference means M minus N. Okay. Actually, matching is the collection of edges. So you have to take all the edges of M that is not present in N, and all the matchings of N that is not present in M, and their union. This is defined as symmetric difference. M minus N union N minus N. Okay, so if we have given two matchings, then we have to take their symmetric difference. Then that symmetric difference will be a path or an event cycle. This we have to prove or disprove. Like if this is not true, then you have to give a counter example. So if anyone of you have solved this problem, then he can say anything, or if you have any idea, any one of you. You can share your idea, whatever you are thinking, you can share, or whatever you have done earlier. Okay. So suppose M and N are two matchings we have, okay, and F is the graph, that is the symmetric difference of M and N, okay, that is M minus N union N minus M. We are deleting the edges, all those edges of N that is present in M, and all the edges of M that is present in N. Since M and respectively N is a matching, every vertex has at most 1 degree. Every vertex in a matching has at most 1 degree, because we know this is coming from the definition of matching, that is the collection of edges where no two edges are adjacent. So every vertex will have at most 1 degree in every matching. So if we will take this F, okay, so suppose one vertex is coming from this M minus N, and one vertex is coming from this N minus M. So this says that every vertex in F will have at most 2 degree. In a matching, every vertex has at most 1 degree. So in F, every vertex will have at most 2 degree. So F is a graph that is the disjoint union of paths or cycles. F is a graph that is the, because every vertex has at most 2 degree. So we can say that F is the graph that is the disjoint union of paths or cycles. Okay, we can decompose F in paths and cycles. Further, every path or cycle in F consists of alternating edges of M minus N and N minus M. Why? You can think about it like take any edge. Suppose there is an edge AB. A and B is the edge of M. Okay. So what can happen? What is the possibility? So B. So we can take the vertex B. Okay. So suppose there is some other edge BC edge from N. From N. AB is the edge of M and BC is the edge of N. Okay. And suppose BC is not present in M. Okay. BC cannot be present in if ABC is, sorry, if ABC is the two edges, AB and BC are the two edges in F, it means that AB is the edge of M or N and BC is the edge of M or N. Both cannot be the edge of same matching, because if it is possible, then that will contradict the definition of matching. So if AB and BC both are the edges of the same matching, so it means that B has degree 2 in a matching, but that is not possible. So the possibility is the only possibility is that either AB will be the edge of M or N, and BC will be the edge of M or N. Okay, so that is why every path or cycle in F consists of alternating edges of M minus N and N minus M. One edge from M, then other edge from N, M, N, M, N, like this. So you can see that if a cycle will be formed, then that cycle will be an even cycle, because alternating edges of M and N are coming. Edge of M, N, M, N, M, N, like this. So if a cycle will be there in F, then that cycle will be even cycle. There is no possibility of odd cycle, because if odd cycle will be there, it means that the edges of some matching will be more, but that is not possible, as alternating edges are coming, alternative edges are coming. So therefore the length of every cycle in F is even, such that M and N contribute equal number of edges. So this symmetric difference contains only the paths or even cycles. No other possibility is there. Okay. Is it fine? Or if you have any doubt in any line, you can ask. Also, I can repeat it. Anyone, you can think. Is it fine for everyone?
Sir, could you repeat the part where you
Yeah, yeah.
said the equal number of edges?
Yeah, equal number of edges. So I am saying that we are taking M minus N and N minus M. Okay. So we are the alternative edges are coming. Just suppose an edge A and B. AB is the edge of M minus N. Okay. So if there is some other edge BC will come. Okay. So that BC will be only from this N minus N. That BC edge won't be a part of this M minus N. Are you getting this? Because if that BC edge is also a part of this M minus N, means AB and BC both are the edges of M. But a matching, in a matching, every vertex has at most 1 degree. So you can see AB and BC are the part of M. That means B has degree 2. This is not possible. So BC must be from N. So that is why alternative edges of M and N are coming. If a cycle will be in F, then only this is the possibility that alternative edges will come. A edge of M, N, M, N, M, N, like this. So if M is coming, then N, M, N, then M will also again come like this. Suppose there is a five odd cycle, like suppose 5 cycle of length 5. It means that there will be some edge, 3 edges of M, means some matching will contain 3 edge and other matching will contain 2 edge. But this is not possible, because suppose first edge will be from M, then second the fifth edge will also from M. It means that 2 edges are adjacent in M, but that is not possible. So odd length
Yes.
cycle is not the possible. Okay.
Okay.
Okay, moving to the question number 2. Does a perfect matching exist for the following graphs? So we have 4 type of graphs. Let me explain all the graphs. Pn is the path, okay, path with n vertices. Cn is the cycle with n vertices. Kn is the complete graph of n vertices, and Knn is the complete bipartite graph of 2n vertices. N vertices above, n vertices below. You can visualize this. Okay, this is the complete bipartite graph. Means every vertex has degree n here in Knn. So you can answer it. So what about Pn? Does a perfect matching exist for Pn?
If n is even,
N is
then
even.
yes.
And what will happen if n is odd? You can
One vertex will be left behind.
yes, one vertex will be left behind. And a perfect matching means a matching which saturates every vertex. Means every vertex will be there. So if one vertex is left behind, then that matching is not perfect matching. So only possibility is if n is even. Okay, you can visualize this by making any n length even length path, even path of even vertices. And what about C by Cn? If n is even, then perfect matching will exist or not? If n is even.
It should, matlab, if n
Yeah,
is even.
yes. If n is even, then a perfect matching will exist, and if n is odd, then a perfect matching will won't exist. You can take an example as 3 cycle K3. So from there you can see that a perfect matching won't exist. 3 cycle you can take A, B, C, then a perfect matching won't exist. That is a 3 vertex cycle. But for every even vertex cycle, even length cycle, you can see that a perfect matching will exist. You can take the matching as alternative edges, as alternating the first edge, third edge, fifth edge, like this. And what about Kn? What about Kn? Perfect matching will exist. Okay, Kn, you can take a 3 vertex cycle is also K3. K3 you can take, that is A, B, C cycle. That is a complete graph with 3 vertex. A perfect matching won't exist. You can see. So and for five, any actually Kn, the perfect matching. Actually, in a matching, you can see uh, that it is a collection of edges such that 2 edges are not adjacent. So you can see every edges there is 2 endpoints for every edge. It means there is 2 vertex for every edge in a matching. So you can see if there are 5 number of edges in a matching, so the number of vertices will be 10. Means if n edges are there in a matching, means 2n vertices are there. So for a matching, the match for any matching, the number of vertices will be even. So a perfect matching, for a perfect matching also, the number of vertices will be even. So for Pn, if you will take an odd, so a perfect matching can't exist. Perfect matching means every vertex of the graph should be present in the matching. So if n is odd, it means that perfect matching won't exist. So only possibility is n is even. Then you have to see that for n is even, it will exist or not. Okay. For n is odd in Cn, also a perfect matching won't exist. For n is odd for Kn, also perfect matching won't exist. But for n is even, it will exist always. Okay. And similarly, Knn, for any n actually it will exist, because you can take, because it is a complete bipartite graph. So suppose above some vertices are there, n vertices, below some vertices are there, every vertex has degree n. So you can take a edges. It is simple. You can visualize this. You can take any example. So for Pn, a path with n vertices, if n is even, perfect matching will exist. If n is odd, it won't exist. And for Cn, a cycle with n vertices, n is even, it will exist. N is odd, it won't. Similarly for Kn, and for Knn, always exist, because it is a bipartite graph and complete bipartite graph. So you can apply Hall's theorem also here, that the cardinality of the above bipartition is same, and the that neighborhood condition also you can apply. Question number 3: a bipartite graph G has a perfect matching if and only if this ns is the same as gamma s that sir has defined in lectures. Okay, gamma s, the neighborhood, all the neighborhood vertices of S. Okay, so you can just take this ns as the same as that gamma s. Okay, so a bipartite graph G has a perfect matching if and only if cardinality of ns is greater than equal to cardinality of S for all S subset of vertex set of G. Okay, G is a bipartite graph. The necessary part, let M is a perfect matching. Okay, any perfect matching we are taking, and S any subset of vertex set of G. Now vertices of S are joined to distinct vertices of NS by M. Okay, because M is a perfect matching, so M is saturating every vertex of the graph. So if we are taking any subset of the graph, vertex set of graph, means M will also saturate this S. M is saturating this S means what? For every vertex of this S, there is an edge present in M. Okay, so if every vertex of this S, if there is an edge present in M, so for that vertex also there is some adjacent vertex, because every edge has two endpoints. So for every vertex there is a edge present in M, means for every vertex there is a vertex present in M. So NS is the same. The definition of NS says that the neighbor vertices, the adjacent vertices of S. So we can take those vertices of M, okay, in NS, which are the other endpoint of the vertices of S, okay, which are adjacent with the vertices of S. So clearly cardinality of S is less than equal to cardinality of NS. Okay, from here it is clear because M is saturating every vertex of S. And sufficient part, saturating means are you getting or not? Saturating means that for every vertex of S, okay, there is some edge in M, such that that vertex is an endpoint. The saturating means this. Okay. This is the meaning of saturation. Sufficient part. Let xy be the partition of vertices of G. If cardinality of NS is greater than equal to cardinality of S, okay, for all S subset of VG, then cardinality of NS is greater than equal to cardinality of S for all S subset of X. We can take S subset of X. Okay, just take this. This is the given condition. So what will we do? We will take S equal to X, because S can be any subset of vertex set of G. So we are taking S equal to X, the one partition. Okay. So we get cardinality of X is less than equal to cardinality of NX, and NX is a subset of Y. NX is the subset of Y, the other partition. So from here, since it is subset of Y, means its cardinality will be less than equal to cardinality of Y. Okay. So from this and this, the first one and the third one, second one, you can see that cardinality of X is less than equal to cardinality of Y. And similarly, when you will take S equal to Y, you will get that cardinality of Y is less than equal to cardinality of X. So from this one, cardinality of X is less than equal to cardinality of Y, and the cardinality of Y is less than equal to cardinality of X. From both, what you get? You get that cardinality of X and Y are same. So cardinality of X and Y are same, and it is this condition is also given here. We are talking about sufficient part, so this condition is given, and the cardinality of partition are same. So from Hall's theorem, G will have a perfect matching. You can apply the Hall's theorem here, Hall marriage theorem. So if you have any doubt, you can ask. In necessary part or sufficient part, any line you can ask. Okay. Moving to the question number 4. Problem 4 says that for k greater than 0, every k regular bipartite graph. K regular means every vertex has degree k. Every k regular bipartite graph has a perfect matching. Okay. So let G be a k regular bipartite graph, and V1 and V2 are the partition of vertex set of G because it is bipartite. So we know that if two partitions are given for a bipartite graph V1 and V2, then the degree sum of the vertices of V1 and the degree sum of the vertices of V2 both will be same, because it is a bipartite graph. It means that, and for every vertex the degree is k. So from there the degree sum of the vertices of V1 will come k times cardinality of V1, and the degree sum of vertices of V2 will be k times cardinality of V2, and both are same. So when the k will be cancelled out, so cardinality of V1 and cardinality of V2 is same. Okay. So now we shall prove it by Hall marriage theorem. So in Hall marriage theorem, we need two conditions. The first condition is that the the cardinality of bipartition, the partitions will be same. So we got that. The second condition is that for any subset of the vertex set of G, the cardinality of that set will be less than equal to the cardinality of the neighborhood of that set. That we need to prove now only. Okay. The equality part we have shown now. The cardinalities are equal. Yeah, anyone is saying anything? Okay. So a matching that saturates V1 will also saturate V2 because cardinalities are same. Okay. Because in a matching, the distinct vertices present in a matching, edges are distinct or vertices are also distinct. So if a matching is saturating the vertex set V1, that will also saturate vertex set V2 because the cardinalities are same and produce a perfect matching. So thus it is enough to verify Hall's condition only. So we are taking A as a subset of V1, any arbitrary set we are taking. Okay, and NA that we have defined earlier, that it is the neighborhood of A, all the vertices which are adjacent to the vertices of A. And EA is the set of all the adjacent edges of A. Means EM means all those edges will come in this set such that one endpoint is from A. At least one endpoint is from A. All those edges will come in EA. Adjacent edges of elements of A respectively. Since G is K regular, so it means that cardinality of EA will be K times cardinality of A because every vertex has degree K. So cardinality of EA will be K times cardinality of A. Also, we know cardinality of EA is less than equal to cardinality of E times NA. Okay, because the NA has because it you can see that all those EA contains all the edges. Okay, but you can see that EA contains all those edges. You can take one vertex only. One vertex you can take. Just take A as a singleton set. So suppose a vertex is there, A, small a is there. So we know that it is a K regular bipartite graph. So degree of that a small a will be K. It means that A is adjacent to K edges. Okay. So NA will contains at least K vertices. NA will contain the K vertices. So ENA will contains all those edges such that one endpoint of those edges are from NA. And NA has K vertices. So clearly cardinality of EA is less than equal to cardinality of ENA. So from example you can see, just taking example, or arbitrarily you can also see that you can take that you know that every vertex has degree K. So the ENA will be always more. You can see it. So we know EA is K times A and ENA is K times cardinality of NA. Again, K will be cancelled out. So cardinality of A is less than equal to cardinality of NA. And A was arbitrarily chosen. So it means that Hall's theorem is, we can apply the Hall theorem now because we have both the conditions that cardinalities of the partitions are same and that for any subset of the vertex set is its neighborhood has more cardinality than that set. So Hall's theorem implies the result that it has a perfect matching. G will have a perfect matching. So you can read it, and if you have doubt in any line, you can ask. Saksham? Saksham, are you there? Ojas? There. Suyash? Suyash, Ankesh, Shivam?
Yes, sir.
Yeah, is it fine? All are sleeping, I think. Ankish, Shivu, Suyash, so just
Yes, it's fine.
yes. Okay. Yeah, no problem. Number 5. Every tree has at most one perfect matching. Okay. So Shivam, do you know anything? Any idea about this problem? Every tree has at most one perfect matching. How will we do it? You can share anything. Hima Sindhu.
So probably by contradiction.
Yeah, but how will we approach? Like, what is the idea? How will we start?
Um,
Every tree has at most one perfect matching. You are saying about by contradiction. It means that you will take two perfect matching, right?
yes.
Then yeah, then some contradiction will come. Then what? So taking after taking two perfect matching, what is the next step? Okay. So we can apply the first that first problem that we have discussed. That symmetric difference of two matchings is the collection of is the disjoint union of path and cycles only. Okay. So let M and N be two perfect matchings in a tree, and F is the symmetric difference of M and N. Okay. Since M and N are perfect matchings, okay, see this line clearly because it is the important. This is the only important line. Since M and N are perfect matchings, each vertex in F has degree 0 or 2. Because when the event cycle will come, so the vertex will have degree 2. Okay, and the suppose one edge, any edge, AB edge is there. Okay, AB edge is present in M. Okay, so some edge can be there, BC edge, such that BC is from N. Okay, and BC is not in M and AB was not in N, then ABC, both the edges will come in F, the symmetric difference, right? Then the degree of B will be 2. Okay, and the other possibility is that AB is present in M and there is no edge, other edge except AB, such that B is the end point of that edge. So N will again contain that edge AB also. AB will be also present in N. Then AB minus AB means what? Only the vertices will be there, isolated vertices A and B. So degree of B will be 0. Why this only two possibilities are coming? Because M and N both are perfect matching, means both are saturating all the vertices of graph. Means for every vertex there is some edge present in M, and for every vertex there is also some edge present in N. So for any edge AB, there will be some edge BC in N for the vertex B, because N has to saturate the vertex B. So it means that there will be some edge such that B will be the end point of that edge. Means some BC will be in N, or the same AB will be in N. So if BC is in N, then the B will have degree 2, and the same edge AB is in N. It means that B has degree 0. So only two possibility in M, F,
Sir,
such that yes.
sir, M and N are the subsets of edge sets, right?
Yes,
And F will also be a subset of edge set. Then how
yes.
come F has a isolated vertex?
Means AB means we are deleting the edges actually. AB, and suppose AB minus AB means we are just deleting the edges. There will be no edge AB. Only the isolated vertex A and B will be there. M minus N, actually we are deleting the set of edges of M and the edges of N, which are common with M, the other set actually. M minus
Okay,
N
sir.
union N minus M. We are deleting only edges, removing the edges, which are common in M and N. Okay.
Yes,
Yeah.
sir.
Yeah. So does every component of F is an, because degree is 0 or 2, it means that there is no possibility of a path. There is no possibility of a path, because every symmetric difference of two matchings are either is the disjoint union of path or cycles. So from here you can see that there is no possibility of a path, so only possibility of a cycle. And since degree 0 is coming for a vertex, means f every component of f will have an isolated vertex or a cycle. But cycle we won't be present there because we are working on a tree, and tree is acyclic. So cycle, there is no case of for cycle there, since the tree has no cycle. So every vertex in f will have degree 0. So you can see it means what it says, that it means that every vertex has degree 0. It means that whatever edges were present in M, the same edges was also present in N. It says this because the degree 0 for every vertex coming. Every vertex in F has degree 0, means whatever edges was present in M, the same edge was also present in N. So this implies that M and N are same matchings, and thus the result follows. Okay, so is it fine? So question number 6, prove that every simple planar graph with fewer than 12 vertices, means less than 12 vertices, has a vertex of degree at most 4. So how will we approach? Anyone? Shivam, Hima, Sindhu, Ankish, anyone?
So for less than like up to 4 vertices, we can directly say, and like after that, we can use that like Euler's formula and then the inequality that is associated with it.
Euler's formula.
If we assume it is connected, like
Yes, yes. So Euler formula we can use only, but that is not the answer actually. You are just saying that we can use this, but how? How will we use? What will become? What is going to come? Are you proving by your contradiction or direct proof you are doing? Anyone else? Any other idea? Okay, any planar graph with n vertices, what is the upper bound for the number of edges?
so 3, like if it's connected, we can say 3n minus 6.
6. Yes, yeah, that will be used.
If it
And
is
directly,
connected.
yeah. So for the disconnected one also we can take the component wise, we can prove. We can prove component
Yeah.
wise because
So
yeah.
then we can say
So
like 3 and
directly for
6
yes, for
component.
directly, yes, we can directly prove for connected graph. So suppose degree of B is greater than or equal to 5 for all vertices B, then the degree sum will be at least 5n. Okay, degree sum will be at least 5n. But the number of edges in a simple planar graph G is at most 3n minus 6. And so the degree sum is at most 6n minus 12. Degree sum means what? 2 times number of edges. So 2 times 3n minus 6 will be 6n minus 12. So at most 6n minus 12 edges can be there, and the degree sum is coming 5 times n. So it at least 5 times n. It means 6n minus 12 is greater than 5 times n. But we have given that n is less than 12. So 6n minus 12 will be less than 5n. So both are contradicting. From here you are getting 6n minus 12 greater than 5n, but from the given condition you are getting 6n minus 12 less than 5n. And this contradict the above conclusion. It means that there will be some vertices for which the degree will be less than equal to 4. Every simple planar graph has a vertex of degree at most 5. The similar argument we will give. Suppose degree of B is greater than equal to 6 for all vertices B, then the degree sum is at least 6n. But we know the degree sum can be at most 6n minus 12, which is less than 6n. That is not possible. So there will be some vertices whose degree will be at most some vertices will have some degree 4, 3, 2 like this. At most 5 only. Yeah, problem number 8. Prove that every disconnected graph with n greater than equal to 3 vertices and m equal to 3n minus 6 edges must be non-planar. So two things are given here. The graph is disconnected, means at least two connected components are there. Two components are there. There can be more than two components. And the second condition is given that the number of edges is 3n minus 6. And then we have to prove that graph will be non-planar. Okay. So since that, suppose we are proving by contradiction, so we are taking that G is planar and G is disconnected. So we are taking two connected components. Okay. We need two connected components of G. So take any vertex of G1 and take a vertex Y of G2. Then add the edge XY. So look at the graph G union XY. It is a connected graph and it is still a planar. Why? Because this G1 was planar, G2 was planar, and we are just adding one edge X and Y, XY edge. So G union XY is a still planar and it is connected graph. So the number of edges of this graph will be at most 3n minus 6, but we have given that G has the edges, number of edges 3n minus 6, and we have added one more edge. So 3n minus 5 it became now. So with 3n minus 5, we cannot get any planar graph. With 3n minus 5 edges, we cannot get any planar graph. So G union XY having 3n minus 5 edges contradicting the maximality of M, because the maximality of M means M can be at most 3n minus 6. It is more than 3n minus 6. So you can see you can see that if it will have more than two components, like three components are there, then G1, G2 and G3, then you can add one edge between G1, G2 and one edge between G2, G3. Then 3n minus 5 will become 3n minus 4. Then again you will get the contradiction, because the 3n minus 4 is also more than 3n minus 6. So number of components will increase, so number of edges will also increase. So that will contradict the maximality of M. So we have proved for only two connected components. You can take arbitrarily k components and then you can prove that 3n minus 6 plus k edges will come here. That will contradict the maximality of M. So G cannot be planar. So G must be non-planar with if G is disconnected and the number of edges is 3n minus 6. Okay, from here a question comes that you can draw some graphs. Okay, you can draw some graphs like with 3n minus 6, exactly 3n minus 6 graph, 3n minus 6 edges, and the graph is connected. A graph is connected and having 3n minus 6 edges with n vertices. You can draw such graph. You can try. Okay, problem number 9. The complement of each simple planar graph with at least 11 vertices is non-planar. So we have given a graph, okay, and the graph has at least 11 vertices, means more than 11 vertices or 11 vertices, and then that graph is planar. It is also given, and now it says that take the complement of the graph and prove that that graph is non-planar. So we know, we have one idea that if we can prove that the complement of that graph has more than 3n minus 6 edges, 3n minus 6 edges type things, so then we can say that yes, complement is non-planar. So you can see that any a planar graph with n vertices has at most 3n minus 6 edges. Hence, each planar graph with 11 vertices will have at most 27 edges. 3 times 11 minus 6 means 27 edges. So any planar graph you can take with 11 vertices that will have at most 27 edges. And since k11, so complement of that that graph will have at least 28 edges, because any graph and its complement, when you will take any graph and its complement and their union, it will become a complete graph, right? So when we are taking 11 vertices planar graph, then and then we are taking its complement, then their union will be a complete graph of K on 11 vertices. So we know that K11 has 55 edges, and out of 55 edges, 27 edges has gone for this planar graph on 11 vertices. So complement of that graph has at least 28 edges. Okay, 28 edges at least. So this 28 edges is greater than this 27 edges, because this is at most 27 edges and this is at least 28 edges. So clearly that complement will be, okay, because it is contradicting the maximality of number of edges for a planar graph. Okay, so this uh, complement will be non-planar. So this we have proved for our graph with 11 vertices, exactly 11 vertices. What about the graph with more than 11 vertices? So for that, you can take this. For ng greater than 11 means number of vertices is more than 11. So you have a graph, okay, and the number of vertices is more than 11. Then choose any 11 vertices and take the graph of inducing by those 11 vertices. Okay, so that is a subgraph of that graph we have given. Okay, so that subgraph is since the graph G is planar, so its subgraph will be also planar. So that you have chosen some 11 vertices and the induced subgraph with those 11 vertices, that subgraph will be planar. So when you will take the complement of the given graph, so actually you are also taking the complement of that subgraph. So that subgraph complement of that subgraph will be non-planar. So that given graph, the complement of that given graph will be also non-planar. Means if graph G has a subgraph which is non-planar, then the given graph is also non-planar. So we are proving through this that if you have given a graph with more than 11 vertices, then induced subgraph, take a induced subgraph with any 11 vertices, okay, and then take their complement, that will be non-planar, and then you can say that the complement of the given graph is non-planar. Okay, so this is the idea.
Sir,
If you have, yes,
sir, in the seventh question,
seventh question, yes.
sir, you said in case the graph isn't connected, we can still
Yes,
do
yes,
it. We can still do it by considering the complement is connected.
yes.
Sir, but how can we be sure that the complement is still planar?
No, this is not about the complements. Question number 7, components. Are you saying components or complement?
No, sir. Like you said, I mean, the Euler's formula is applicable only for connected graphs, right?
Yes.
So you said in case of disconnected graphs, we can still take that the complement is connected. So
No, complement
do
is
that.
complement is connected. Yes, complement graph will be connected.
But how are we sure that the complement graph will be planar also, sir?
I'm not saying that the complement graph will be planar.
Like sir, for complement, we want to apply the Euler's formula, right? So if we want to do that, then we have to make sure that that graph is planar.
Yes. We have to make sure. Yeah, we have to. No, actually, for this problem 7, when the graph will be disconnected, we can take every component. Not we won't take complements. We will just suppose G is disconnected. So there will be some components like G1 and G2. Then G1 is connected. Then we can prove for G1 that some vertices. Suppose we can take for G1 that every vertex of G1 has degree more than equal to 6. Then we can prove that G1 has subvertex has atmost degree with atmost degree 5. Similarly, for G2 we can prove. So then we can prove that G1 union G1 and G2, that graph G has also some vertex with atmost degree 5. So we
Oh,
can
okay.
work on the component.
Yes, sir. Okay.
Yeah.
Got it.
And here we are taking the complements actually. Okay. So question number 10, show that if a shortest cycle in a planar graph, what we mean by shortest cycle means a cycle with shortest length in a graph. Okay. So we have given a planar graph G and a shortest cycle with length K. Then we have to prove that the number of edges will be less than equal to K times n minus 2 by K minus 2. M and n are the number of edges and vertices respectively. So anyone who has some idea, this is a good question. Any idea, any line, any statement you want to share, you can share. Then I will give you some hints, then you can approach yourself. Okay. So what is the idea for this question actually? So what will we do? We will prove for those graph which are connected first. Okay. So we will prove this result for those graph which are connected. Okay, so first we shall prove for connectedness, then I will discuss about what we will do in the case of disconnectedness. So suppose let G be connected. Okay, so boundary of each face is either a cycle or contains cycle in a planar graph. Okay, so if any boundary, any face is either a cycle or contains a cycle, and we have given that every shortest cycle shortest cycle has length K. So any cycle in the graph G, their length will be more than or equal to K, right? Because the shortest cycle length is K. So any cycle in G will have length at least K. So if any face is either a cycle or contains a cycle, it means that every face has at least K edges, because every face containing a cycle or it is same as cycle. So it means that every face has at least K edges. Okay, because every cycle has at least K edges, because the shortest cycle length is K. So it means that if F is the number of faces, so it means that at least Kf edges are present there. Okay, at least Kf edges are present there, because every face contains a cycle or it is same as a cycle. So it means that there is at least Kf edges. Also, every edge can be in the boundary of at most two faces. So suppose two faces are there, then their boundary, if some edge and both the faces are sharing each with a boundary an edge is present there on the boundary of both the faces. It means that sorry. Yes, yes. Also, every edge can be in the boundary of at most two faces. So it means that if you have given a face, so any edge can be on the boundary of that face, and with that edge there can be some other face also. Okay, so two faces can share one edge. This is one possibility, and they may not share, or if they are sharing, then they will share via an edge. Okay, so it means that every edge can be in the boundary of at most two faces, and the correspondence in this case is at most 2 times m. M is the number of edges, means the number of faces. We are counting the number of faces and the number of edges through that, and from here every edge is in the boundary of at most two faces. So from there, if we will count all the number of edges, it will become 2 times number of edges, 2m. Therefore 2m is greater than equal to kf, because at least kf edges are also is already present there in the graph. So 2m is greater than equal to kf, and by Euler's formula we have given n minus m plus f equal to 2. So from here we can apply that n minus m plus 2m by k is greater than equal to 2. We can take the maximal possibility of f is less than equal to 2m by k, so we can take 2m by k directly. So that is the maximal the maximum value of f. So n minus m plus 2m by k is greater than equal to 2. From here you will get that m is less than equal to k times n minus 2 by k minus 2. So we are counting the number of edges in the graph through the faces, because the first one we have counted by since every face is either a cycle or contains a cycle from here, and from here that every edge can be in the boundary of at most two faces. So and then we have applied by we have applied the Euler's formula. Yes. Now we shall discuss when the graph will be disconnected. So suppose we have two components, G1 and G2. Then we can take more than two components. G1 and G2 are the two components of a disconnected graph G. So for G1, this G1 is connected. Okay. Then G1 has some shortest cycle, G2 has some shortest cycle. Okay. Then we can apply. Suppose G has some shortest cycle of length k. Okay. And G is disconnected with two connected components, G1 and G2. So then that shortest cycle will be either present in G1 or either present in G2. This is the case only. So if G1 has that shortest cycle, now what will we do? We will take one vertex of G1 and one vertex of G2, then we will add one edge through those two vertices. Okay. So we are just adding one edge between G1 and G2. So we can see that still this graph G1 union G2 and that edge with that edge, still it is planar. Okay. And still the shortest cycle length is k. You can see, because we are not disturbing that shortest cycle which was present in G1 or G2, any one of those components, and we are just adding one edge between G1 and G2. We are not disturbing any cycle, just adding one edge. So still it is planar. Now it became connected, and still it has a shortest cycle of length k. Okay. So now we can apply the that we have what we have proved for the connected planar graph. So now the m will be less than equal to kn minus 2. Now you can see the a number of edges of this graph, that after adding one edge is actually the number of edge of G plus 1. The number of edges of this new graph is same as the number of edge of G plus 1, because we have added only exactly one edge. So actually m plus 1 is less than equal to this. So m plus 1 is less than equal to this number, means m is also less than equal to this number. It means that for G also m is less than equal to k times n minus 2 by k minus 2. Okay. So if the graph is G is disconnected, then we can add necessary edges to get a connected planar graph. Okay. Then we can apply this result for the connected graph. Okay, you can read this, and if you have doubt, you can ask.
So what does it mean? Boundary of each face is either a cycle or contains a cycle. So what does it mean by a boundary of a face containing a cycle?
Means suppose it. Okay, just take a graph. Take three cycle you can take. Okay, K3 we are taking A, B, C. How many faces are there?
2.
2. Okay, so just take outside face. The second face, that is not inside that cycle, outside cycle. The
Okay,
second face, yeah, boundary of that face contains a cycle. That K3, ABC.
Oh, okay.
And the first phase is itself a cycle. Contain is either it is same, it is same as the cycle ABC. Okay, so moving to the question number 11. Find the chromatic number for the following graphs: Pn, Cn, Kn, and Knn. I have discussed all these graphs. What are these graphs? So just tell me the numbers. Okay, what is the chromatic number for Pn?
2.
2. Yeah. For Cn?
So 2 and 3 for 2 for even and 3 for
And
odd.
3 for odd. Yes. And what about kn?
So it is n itself. N.
Yeah, n itself, because every vertices are adjacent. And what about knn?
So 2 because bipartite.
Yeah, it is bipartite, so it will be 2. Question number 12. The click number of this question that the for any graph G, okay, the chromatic number of that graph will be less than equal to maximum degree of that graph plus 1. This is done in class. Sir has done this uh, problem in class, so I won't discuss. I will skip this one. You can read from that note, or you can read from that lecture. Okay, give example of a graph G on n vertices such that chromatic number of G plus chromatic number of G complement is n plus 1. Think and tell
So
me.
the complete graph of n vertices.
Yeah, complete graph. Who's told the answer?
So I said it.
Yeah, Shivam. Good. So it will, we can take the complete graph Kn because the chromatic number of Kn is n, and the complement of Kn will be the n isolated vertices only. So we can color that those isolated vertices with one color only. So the chromatic number will be 1. So n plus 1 will come. Good. Other graphs are also possible. You can think. Now the question number 14 is says that draw a triangle free graph having chromatic number 4. Okay, having chromatic number 4. So this is the construction. This is question for construction, and we call it Michalski's construction. Okay, mathematician Michalski's construction. Uh, the use of this construction is that we can construct some graph with a triangle free graph. Actually, a triangle free graph means there is no cycle with length 3. There is no cycle will be present with length 3. So triangle free graph we can construct with, and we can construct such graph with high number of vertices, means large number of vertices, and the chromatic number with chromatic number very small chromatic number, less chromatic number. So we can we have constructed a graph here with 11 vertices. Okay, 11 vertices. Yeah, 3 to 5, 5, 10 plus 11. 11 vertices. The number of vertices is high, but you can see the chromatic number will be 4 here. So this is the use of this construction, that you can construct a triangle free graph with more number of maximum number of vertices and less number of chromatic number. The chromatic number will be less. So this is the use of this construction, and the construction is given very easily. It is done, so you can read yourself. This is your homework, or you can skip also because this is not in the syllabus. But if you want to read, you can read from here. And if you have any doubt in this construction, then also you can ask. So this is done for this graph only. Okay, so similarly other graphs you can also construct, but there is some general formula or general construction method. Okay, you can find on internet also. You, if you want, I can share with you. You can read yourself. This is your homework. Yeah, but this is not in the syllabus, so don't take it seriously. It is just on you. If you want to read, you can read. This I have skipped this question 12, because it was done in the class. So if you have doubt in any question, you can ask now. Any question from 1 to 14, or later also you can message me or mail me. Yeah, Hima Sindhu and anyone. Saksham is sleeping, I think.